Hello everybody, this is Dilix from Northern Mechatronics, or NMI. Today we'll be showing how to set up the NM180100 module to take pictures and run a machine learning model to run inferences. The task that we'll be dealing today is image recognition. Image recognition in machine learning centers around the idea of predicting what class an image is part of. If we were to take a picture of a car or a phone, then the machine learning model should identify what kind of object is within the image. But today, we'll focus on a slightly easier task related to image recognition, which is called digit recognition. So you'll see here we have a bunch of digits written here, from 1 to 9, and then we have the digit 0 here. In addition, we have our module, which is on our evaluation board, or EVB, and we have our camera right here. And this is our USB cable, which is plugged in to our laptop right now. So let's go over some of our equipment today. First of all, we have our NM180100 module, which is on our EVB. We also have our ArduCam. In fact, it's actually the ArduCam Mega Spy camera. And the pinouts, which will be located in the documentation or README on how to connect the camera to our EVB. And we also have our USB cable that's hooked up to our laptop, and we're going to connect it to the EVB. So let's bring these a little closer so you can see. We're going to connect our ground and power source. You can see that we're connecting it to 5 volts. Next, because we're connecting via SPI, we're going to connect our clock, MOSI, and MISO. So these 3 wires here. And lastly, we have our chip select here. This will go in pin 11. Awesome. So before we even turn this on, let's connect the USB cable to the EVB. Great. And now let's switch it on. And the blue light is on, means that it's ready to go. So before running the model, we are going to demonstrate how to set it up. As we mentioned in our documentation, once you have trained and quantized your model, you will write that model to a .tflite file and convert it to a hexadecimal character array. That is done by running xxd on your tflite file, which can then be written to a CPP or CC file. Afterwards, you will connect the module to your computer and connect the camera to the board. Before we start running it, we need to check if the model settings are correct. Let's pan over to our model settings source files and header files. In the header files, we can see a couple of important information. First of all, we note the input tensor. This is what's coming into the model. We see that the number of columns and the number of rows are both 32, and the number of channels is 3. This means that the model accepts a 32 by 32 RGB image. As well, we have information about the output tensors. We see that we are getting 10 categories, each category representing a particular digit from 0 to 9. There's an important observation that we need to make here. If we pan over to our source file, we can see that the digit number 0 is not the first element in the array. In fact, it's the last element. The first element in the array is digit number 1. This is important information because we need to be able to print out our predictions correctly. In addition, we also have information about our model. After running xxd, we can see our quantized model in a hexadecimal character array. Each element represents a byte in hexadecimal. The next variable is the length of the array. Here, the length of the array is 378,696. In other words, the model size is around 379 kilobytes. And last but not least, the TFLM source file. This contains all of our information and how we set up the model in the first place. A couple of things here to remember. First of all, we need to import our model settings as well as the model itself. Second of all, we need to define a couple of functions. The TFLM setup initializes and builds the interpreter. The interpreter is what's going to run our model. The interpreter requires a couple of components. First of all, we need to port the model over to a reasonable format. Second of all, the resolver, which defines and loads in the operations that the model needs to perform inferences. Third of all, the TensorArena and the TensorArena size, which stores and declares the size of the input and output tensors. And last but not least, the error reporter, which is similar to printf in C. This allows us to print to the console. After the interpreter has been built, we can finally allocate tensors for the input and outputs and perform inferences. When we perform inferences, we do so under the TFLM inference function. Here, after we capture information from the camera, we copy the image captured from the camera into the input tensor, invoke the interpreter, and finally grab the predictions that comes out of the output tensor. To present the predictions properly, we need to be able to write a function that presents the predictions in a readable format. This is done through prediction results. Prediction results is a function that resizes the scores from a signed integer format to an unsigned integer format. This makes it easier for people who want to view the prediction results and presents the results in a much more readable format. So now that we've gone over our model settings, we are now going to build the executables. Our TF Lite app model is based on NM180100, and we are going to build and load it into the EVB. To start, we're going to go into CMake, and we're going to do a clean build. To do this, we're going to click on Build All Projects, and we're going to hit Clean Rebuild. We note that this process is going to take some time, perhaps a couple of minutes, and we're actually not only building, but we're also loading and deploying it on our module. Awesome. Once it's done building, we can go over to run a debug session. We can go under Run and click on Start Debugging to start a debug session. Once the debug session has started running, we can go over to our serial monitor, and we are going to set a couple of settings here. We're going to change our port to indicate that we want to use the module. Here it's indicated as USB modem, although this will depend on what kind of computer you're using. We are also going to set the baud rate to 115,200. Afterwards, we're going to click Start Monitoring. You'll know that the module is working properly if you can hit the Enter button and a bunch of timestamps come out. So we know that the module is currently working. So now that we built the executables, we can now start finally running inferences on the model. To do this, we're going to place our camera over the digit number 1. We're going to center it like that. Afterwards, we're going to write cam capture. We'll wait for the inference to be provided. And as you can see, the predicted digit is number 1. Now you might ask, how do we know this? What does the other information provide? In the second line here, we can see that the score is 179. Now what does 179 mean? For purposes of quantization and for Tensorflow Lite for microcontrollers compatibility, our inference input types and output types are 8-bit signed integers. But 8-bit signed integers are ranging from -128 to 127. So, to make it better readable, we need to resize the ranges from -128 to 127 to 0 to 255. We can also see some of the categories and the raw scores that come out of the model. For instance, for the classifier 0, or the digit number 0, we can see that the score was 0. Remember that the prediction shows you how likely the digit was recognized within the image. The higher the score, the better the prediction. We can also see other numbers as well, such as 7, 8, and 9. And these digits have very, very low scores, as you can see here. Once the inference has finished, it will print out a line saying inference done. This allows us to run further inferences. So let's hold the camera here for digit 2, and let's hit cam capture again. And as you can see, the predicted digit is number 2. How about digit number 3? And the predicted digit is number 3. Now this is great, but there's still a huge problem. In most cases, the camera is not normally oriented like this. Sometimes there might be skews or rotations within the camera. So what happens if we rotate the camera slightly? What will that give? Let's try it with digit number 5. Let's hit cam capture again. And the predicted digit is number 5 as well. Great. How about digit number 6? Digit number 6 is predicted quite well, with a score of 255. How about digit number 8? Digit number 8 is predicted relatively well. The confidence level is slightly lower than what we would like it to be, but the score for the predicted digit number 8 is still quite high. And last but not least, let's try digit number 0. And the digit number 0 is predicted quite well.